Alright, in this video I want to talk about some of the basic conversion math problems in the dosage calculations test that you'll see. Again, like I said in the first video, this is going to be very specific to what you're going to encounter at Cox College. In fact, it's based completely off of the mathematics or dosage calc curriculum at Cox College. So I imagine it's pretty similar nationwide, but there may be some variances, so expect that if you go to another school. Alright, so let's start off pretty basic here. We've got grams to kilograms right here. And basically whenever we set this up in our dimensional analysis problem, you can do it one of two ways, right? You can go about it the chemistry way that you learned in Chemistry 210, I believe it is. So let's say we've got 3,500 grams, and I want to know how many kilograms that is, right? The chemistry way, you would actually start with your given, which is this right here, the 3,500 grams, and that in a dosage calc mathematics or dosage calculation math problem, your given is generally going to be your doctor's order. So, but in this case, it's the 3,500 grams, and then we're going to enter in our conversion factor. The conversion factor is going to give us what we want as our final answer. In this case, it's kilograms. So when I say conversion factor, I mean how many grams are there in a kilogram. So if I have 1 kilogram, 1 kilogram here, how many grams are in that? Well, we know because we memorized it, and it's the metric system, and it's simple, that kilo just means 1,000, and this G here stands for grams. So that means 1,000 grams. 1,000 grams. So I know that for every 1 kilogram, I have 1,000 grams. Alright, so basically what you do now is you just plug it into your calculator. You pull up my single one-function calculator that Cox College requires you to have. So you've got 3,500 times 1. You don't actually have to do this times 1, but I'm doing it just to show fluency. Divided by 1,000. It's going to leave us with 3.5 kilograms. 3.5 kilograms. So this is a weight, so we go out to the thousandths place, which would be right here, and we round to the hundredths place, which is right here. And it's pretty much solid and done for us anyway, so we don't have to worry about doing that. So this is one way to do this basic conversion. And if you look in your dimensional analysis book, or if you've had it in the class taught here at the college, you're probably used to doing it just about the exact opposite way that you see it done here. And I didn't put my units there. It's really important, 3.5 kilograms. Either way's fine. If you look at the way I did it, grams cancels out here, grams cancels out there, I'm left with kilograms. The beauty of dimensional analysis is that it really doesn't matter what order you put your steps in, just as long as everything cancels out and you end with the desired unit that you were looking for. So I could have done and set this problem up this way. I could have done 1 kilogram over 1,000 grams times 3,500 grams equals blank kilograms. Now I know this equals blank kilograms because my grams here cancels out and my grams here cancels out. You can do this either way, especially whenever you start putting in, 4, 5, 6 conversion factors to get to your final answer. Dimensional analysis is nothing more than a means for us to sort and organize our division and multiplication. So it doesn't matter what order it goes in. If you like to do it this way, great. I'm going to have the tendency to do it this way right here, just because as you're moving into first semester nursing school, generally you've probably done 200, 300, if not more, dimensional analysis chemistry problems set up that way. So when I was in the military, we had a saying called "keep it simple, stupid." That's what I'm going to attempt to do here. But you may see me do it and organize it both ways from time to time. If you do it the way I did it in green up there, a quick, easy way to see if yours lines up like mine is just to flip the way I do my problem backwards. So if you look at that again, 3,500 was over at the end of the problem in this one. My 1 over 1,000 was at the beginning. Over here, the 3,500 is at the beginning. 1 over 1,000 is at the end. That's generally how you'll see my problem set up, is the exact inverse of yours or exact opposite of yours if you're doing it that way. So let's do another one, maybe one that's a little bit less easy than grams to kilograms. Here we've got kilograms to pounds. With this one, we've got to remember the metric system and the U.S. standard system. So we know that with every 1 kilogram that I have 2.2 pounds, right? That's my conversion factor. So I'm going to start with my given, and let's say that you're given, I don't know, 16 kilograms, right? And we want to know how many pounds that is. I would start with my given, which is this 16 kilograms, or like I said, you can start with your conversion factor. So we've got 16 kilograms, my given, multiply that by our conversion factor, which is for every 1 kilogram, I have 2.2 pounds. Now you may be saying, what the heck just happened there? You had kilograms on top up here and pounds on bottom over there. Why'd you flip them whenever you worked this out? Well, the reason I did is, if you remember, I said dimensional analysis is nothing more than a means to sort our multiplication and our division. So I flipped these because with kilograms on bottom, it cancels out my kilograms here, and I'm left with a unit of pounds. I know with dimensional analysis, if I always set the problem up correctly that way, that it is going to organize my multiplication and division in a manner that will give me the right answer every time. That's why we use dimensional analysis. It's supposed to be a little bit intuitive, but I think sometimes we make it out to be this giant, confusing analytical animal that it's really not. It just organizes our multiplication and division. So we're left with pounds as our final answer. That's what I was looking for, so I know I set my problem up right. Grab my calculator here, plug that in. I've got 16 kilograms times 2.2 divided by 1. You don't have to do the divided by 1, but I'm doing it again just to show complete transparency of the problem. I'm left with 35.2. So I have 35.2 pounds is what the equivalent of 16 kilograms is. So easy day, problem done, right? Let's switch to one that's maybe a little bit more complicated. So here we have a word problem. Everybody loves word problems, I know. This one says, a newborn infant weighs 2,675 grams. The mother wants to know what its weight is in pounds. The nurse tells her that the weight is blank. So there's a couple different ways you can do this. You can do it in pounds and ounces. Ounces would obviously require you to know a little bit more about the conversion factors as far as how many ounces is in a gram and so forth. But let's just put it in pounds. So let's start with our roadmap for this problem, because this is going to require a few steps, right? I have my given, which is that this baby weighs 2,675 grams. So I'm starting in grams, all right? I know from grams I'm going to need to go to pounds. Well, I don't know how many grams are in a pound, but I do know how many pounds are in a kilogram. So I can go from grams to kilogram. And then once I have it in kilograms, just like I did in the problem above this one, I can go to pounds. I guess that has 2 L's. Let me erase one of those. All right. So I can go from kilograms to pounds. So let's do that now. All right. 2,675 grams times, I know for every 1 kilogram, I have 1,000 pounds. Put an S on it. There we go. Pounds. And then I know that for every 1 kilogram, I have 2.2 2 pounds. That's going to equal blank what? Well, let's cancel our units out. I've got grams on top here, grams on bottom there. I'm not quite sure. I think I really labeled that pounds. This should be grams. Let me correct that. I don't want to confuse anybody. That should be grams. That's what I meant to write, but my handwriting's kind of chicken scratch. So I have grams on top here, grams on bottom there. I have kilograms on top here, kilograms on bottom there. And then I have pounds, and nowhere in my equation here do I have pounds on the bottom to cancel out this pounds on the top. So that means my end unit is going to be pounds. And that's what I was looking for, so I set my problem up correctly. Now all we have to do is plug that into our calculator. 2,675 times 1 divided by 1,000 times 2.2 divided by 1. Alright, so I'm left with 5.885 pounds. Now this is a weight, so we know on weights we go out to the thousandth place, which is where the 5 is at, and we round to the hundredths place, which is where the second 8 is. The 5 is greater than 1, or it's the thousandth place is greater than 5, so I'm going to round this 8 up to a 9 and be 5.89 pounds. So 5.89 pounds. Easy enough, right? That's how you go from grams to pounds. In second semester, you'll be, or at level 2, you'll be expected to go to pounds and ounces, and there's an extra step added in there that we'll get to in a different video. Next, let's move on down. We've done weights. Now let's do volumes or liquids. So I have milliliters here. Let's say 1,200 milliliters. And I want to know how many liters that is, right? I want to know how many liters is in that 1,200 milliliters. Easy enough. We start with our given, which is the 1,200 milliliters. We multiply that by our conversion factor. Just like there's 1,000 grams in 1 kilogram, I know that there's 1,000 milliliters in 1. I know there's 1,000 milliliters in 1 liter. Pardon me there. So just like there's 1,000 grams in 1 kilogram, I know there's 1,000 milliliters in 1 liter. So 1 liter here on top and 1,000 milliliters on bottom. If I set it up this way, then my milliliters will cancel out, and I know I'll end with the right answer. So this will equal blank liters. Grab your calculator. 1,200 divided by 1,000 equals 1.2. 1.2 liters. So that's basically essentially going from milliliters to liters. Next, let's go from ounces to milliliters. So I know that for every 1 milliliter, let me switch colors. I know that for every 1 milliliter, I have about 30 ounces. It's actually like 29.5 something, whatever. But in nursing school, or at least at Cox College, we round to 30. So we say that for every 1 milliliter, you have 30 ounces. So let's say that I've got 216 ounces, and I want to know how many milliliters that is. Well, I'm going to start with my given, which is a 216 ounces. And I'm going to multiply that by my conversion factor, which is for every 1 milliliter, I have 30 ounces. My ounces here are going to cancel out, and I'm going to be left with milliliters. So milliliters is what I was looking for. I don't know how many milliliters there were. So I set my problem up correctly. So grab your calculator, so you can see it there. 216 divided by 30 and I have 7.2. Now, on volumes or on liquids like this, you go out to the hundreds place and round to the tens place unless the number is less than 0 or less than 1. So if this was 0.2, I would go out to the thousandth and round to the hundreds. And that's because we can use a TV syringe and be more accurate on volumes that are less than 1 milliliter. But this is not. It's 7.2 milliliters, so we're just going to round to the tens place. All right, so let's go here, 7.2 milliliters. And it's really important, let's talk just for a second about that. If this was, let's say, if our answer was 0.2 milliliters, it's really important to put this 0 in front of there. That prevents a lot of medical errors and mistakes. So putting that 0 there is really important. So hopefully if you do the problems backwards from the way that I do it, which is probably the way some of you at Cox College do, you're starting to get the trend that it is the same, doesn't matter what way you set the problem up. I could have done this problem just as well, started at 1 milliliter over 30 ounces, multiply that by 216 ounces, 16 ounces, and my ounces are still going to cancel out here. I'm still going to be left with milliliters, and that's still going to equal, running out of page a little bit here, scroll over, that's still going to equal blank milliliters. It's supposed to be an M. That's still going to equal blank milliliters. It's still going to equal the same amount of milliliters, either 7.2 milliliters. So it works out the same way no matter how you set the problem up. That's what's so great about dimensional analysis, is it doesn't matter, say we've got a problem that's 14 steps long, and you're like, I don't know where to begin. Well, it doesn't matter where you begin, just start somewhere. And as long as you label up, or correctly label and group your units to how you want them to cancel out, you're going to get the right answer. So let's move on to a more difficult one here. And in this one, again, we're wanting to know how many milliliters we have in 2.5 ounces. Well, this is easy. We set it up the exact same way. You can either set it up as 2.5 ounces, which is our given, times for every 1 milliliter you have 30 ounces, or you can set it up as for every 1 milliliter you have 30 ounces times 2.5 ounces. Both are going to cancel out the ounces, leave you left with milliliters. Both are going to give you the right answer. So you go and plug this in and do it here. 2.5 divided by 30. Alright, so this is one of those situations where our answer is less than 1 milliliter. So we are actually going to go out to the thousandths place here and round to the hundredths place. So I have 0.083. 3 is less than 5, so I'm not going to round. My final answer will be 0.08. Alright, that's 0.08 milliliters because my ounces canceled out. Now, if you were to go through here and cancel this out and maybe say that you're still left with milliliters somehow, maybe say you've got milliliters on bottom accidentally and ounces on top, and your milliliters and your ounces won't cancel out, that means you set your problem up incorrectly and you need to go back and do it and look at it again. So before you're done with any problem, make sure your units cancel out. That's a great step to make sure and ensure that you've done the problem correctly. All right, let's keep going here. Micrograms to milligrams and milligrams to micrograms. So if you remember from chemistry, you probably had to remember, that for every 1 gram you've got, or for every 1 kilogram you got 1,000 grams, and for every 1 gram you've got 1,000 milligrams and picograms and micrograms and so on and so forth. And maybe even your chemistry teacher had you remember that for every 1 gram, you have 1 times 10 to the 6 micrograms, right? And hopefully, they did, you remember that. But in the world of nursing, we don't use this little upside down H. And we certainly don't use scientific notation too often. If this is simpler for you right here, which first semester it was for me, I was coming fresh out of chemistry. I practically have a chemistry degree, so scientific notation and the Greek symbols are very familiar to me. So first semester, this was easier for me than the shortcut that I'm going to show you. But if you didn't, and this isn't tattooed in your brain, here's an easier way to go about it. Let's say that we have 13 micrograms. And in nursing, we call micrograms mcg instead of the Greek symbol there. Pardon me. So what we're going to do is do 13 milligrams with our given, and I want to know, or micrograms, pardon me, and I want to know how many milligrams that is. We know, and this is a shortcut, that for every 1 milligram, that there are 1,000 micrograms. So my micrograms are going to cancel out, and I'm going to be left with blank milligrams. All right, let me back up for a second here. If you're of this type of brain and mind and thinking, and that is tattooed in your brain, then don't fight it. Start with micrograms. I have 13 micrograms, mcg. Multiply for every 1 gram. I have 1 times 10 to the 6, or a 1 with 6 zeros behind it, micrograms. And then just go from grams to milligrams. I know that for every 1 gram, I have 1,000 milligrams. There's nothing wrong with that. Both will get you to the exact same answer. Furthermore, it doesn't matter what order I put this in. I could have started with 1,000 milligrams, or in 1 gram, and then said that for every 1 gram I have 1 times 10 to the 6 micrograms, and then multiplied that by my given, which is 13 milligrams. You'll get the exact same answer. That's the beauty of a dimensional analysis. It doesn't matter what order you set it up in. All that matters are that your units cancel out. I'm left with milligrams. So let's plug this into our calculator. And I will say to the people that are used to doing this in chemistry, at least a small portion of reasons people fail this calculation test is just simply because they entered it into their calculator incorrectly. And you're adding an extra step here, which in turn adds an extra opportunity for you to make a mistake and enter it into your calculator wrong. Let's say you accidentally enter in 5 zeros thinking that you pressed the 0 button 6 times. That would give you the wrong answer. You would get the question wrong. And at Cox College, at least, 1 or 2 wrong answers is the difference between passing and failing, literally. So fewer steps is better. So 13 micrograms times for every 1 microgram, we have 1,000 milligrams, or micrograms. That leaves us with 0.013 milligrams. So this is a weight. Milligrams is a weight, so I'm going to go out to the thousandth place, round to the hundredths place. 3 is less than 5, so I'm going to have 0.01 milligrams. Simple enough, right? Well, I think that's kind of a lot to digest for one sitting at least, so I'm going to go ahead and stop the video here now and make this into a part 1 and a part 2. Go back through this video if you need to, if you have questions. Go ahead and and rewind, pause, listen to things I say twice maybe, do the problems on your own the next time, see if you get the right answers. Part 2, we'll get into more milligram to micrograms, but we'll be talking about actual drugs. So tune into part 2. We'll finish with the rest of level 1 problems at Cox College and dosage calculation.